Hello, this is Jack Jackson back again. We're going to be looking at improper integrals in this video. Now, in the exercises that we had above, we always insisted on making sure that when we use the fundamental theorem of calculus to calculate definite integrals, the integrand, the function we were integrating, absolutely must be continuous on the closed interval between the lower and upper limits of that integration. This is absolutely necessary in order to apply the fundamental theorem. So you have to check that condition before you can go any farther. And the definite integral of this type, where the integrand is continuous on the closed interval, will have a value, okay? And that is a integrable function, and that's known as a proper integral. So there's a natural question that then arises. Well, what happens if the function is not continuous on the closed interval? Maybe at one or both of the endpoints, or maybe it has a limit going to infinity or negative infinity as it approaches one of those ends. Some cases it turns out that the integral is actually undefined, but there are other cases where we have a technique that we can apply to make sense of what would be called an improper integral in that situation, right? So let's take a look at this. So let's look at a couple of specific cases here. So the first case we're going to look at is if a function f is continuous on a half-closed interval from a to b, including a but not b. Well, if that's the case, then it's continuous on any closed interval a to c, where c is between a and b. So if c is any number in the interval from a to b, including a, not including b, something between a and b there, then the function is continuous on that closed interval. Well, then, if you take the integral from a to c of f of x dx, that integral is defined for those c's. And then what we can do is, guess what we do all the time in calculus? Take it to the limit. So we take that limit as c approaches b, in this case from the left side only. And if that limit, so this integral part will exist because our fundamental theorem says it's going to work. We may or may not be able to do it. If we can get our hands on an antiderivative, then we know what that is right there, but it'll be a function of c, okay, because c is a variable we introduced. But then it may be that function of c, we can take the limit as c approaches b from the left, and if that limit exists, then we say that improper integral that we started with converges to that limit, and it actually has an actual value. On the other hand, if that limit may go to infinity, in which case we say that integral diverges, or any other way that limit might not exist, then we would say that integral does not exist. Okay, so that's the basic idea. We can do the similar thing here coming from the left side. So if we've got an interval from a to b, open at a, closed at b, and if we pick any c between a and b, if the original function is continuous on this interval right here, this half-closed, half-open interval, then it's going to be continuous on this closed interval where c is its number between a and b. And once again, we do the same thing. We integrate, we replace c with the lower end, the a with the c, and then the integral from c to b of f of x dx does exist, and then we take the limit of that as c approaches a. This time c is above a, so we're approaching a from the right side. And once again, if that limit exists, then this improper integral converges, and we've got it. It works out. So let's take a look at what this does here. So actually, you know what? I'm gonna demonstrate something here. Okay, so let's look at this as an example. So suppose we want to find the integral from 0 to 4 of 1 over the square root of x dx. So notice that this integral is defined and continuous for x in the interval from 0 to 4, but it's not continuous at 4, and it is undefined there. It actually has a vertical asymptote there at x equals 0. Now, for any value c from 0 to 4, we see that this integral from c to 4 exists, and it can be represented as an area. So we see that the function, the integrand, is continuous on the closed interval from c to 4, and thus that integral exists and represented by an area. And so so what we can do here is we can look at a variety of c values. I'm going to go to the between 0 and 4 for all these guys, and they're approaching 0 from the right. So we'll start pretty far to the right at 3, then go down to 2, 1, a half, 0.1, and 0.01. And graphically, here's what we're looking at. So at c equals 3, this is the integral from 3 to 4, and we can see that as this interval. This is the curve right here, has a vertical asymptote here at 0, and 4 is right at the edge of the screen here. The x-axis is kind of here in red. You can kind of see that. And so this area right here, almost like a rectangle, but not quite. The top is a curve. And, oh well, it comes out to be something there. Was it, say, 0.58 something? Okay, that is what that area turns out to be. Okay? Now what we do is we just take this one at 3, and we move it a little further to the left, and that picks up some more area. So now we have all this area here. So we move it from 3 over to 2, and now with the smaller c, we've got a bigger area there. So that area is now up to 1.1 something. Okay? And then we could even move even further to the left with c to let it go to 1, and now we've picked up an even bigger area. So now we're going from 1 to here, and it looks like that's just 2. That's interesting. So 2 for that area. Okay, and then if we go to a half, we've brought it over even further from 1 over to 0.5 there, and that's about looks like 2.5 something there. That's an area. Well, what if we go a little further to the left? Now we've gone over to 0.1. We can do that one as well. It's 3 point something. There's an area there. What if we go even further to the left? What if we go to 0.1? Now this is going probably up off the screen here a little bit, but it does have some finite area. Looks like it's still under 4, about 3.8 or so. We get that area. Well, what happens if we take it all the way in? And well, we're talking about a limit process here. Okay. So now, if we wanted to find the exact values of each of these things here, what we're doing is we're finding the integral from c to 4 of 1 over square root of x dx. Well, 1 over square root of x is x to the negative 1/2, so we can just apply the power rule. And so we add 1 to the power. 1 plus negative 1/2, that's 1 minus a half, is a half. That is incorrect, what I have here. So let me fix that. This should be, come down here. So this should be 1/2. And this should be 1/2. Let's see if this still works out. Okay, and then we put in 4. This is, let's get this to be 1/2 here. Okay, so what happened there? I think I must have copied and pasted something from earlier and it didn't copy over correctly. Or didn't get back to it. So this should be 1/2. And the top is 4 there, and then this is 1/2, and this is 1/2. Now, they both have the 1/2, so I can factor that out. 4 to the 1/2 is just simply 2. This is still 1/2 here. And this is 2. And it's minus c to the 1/2. Now, the question is, can we take a limit here? Get this to change what I want it to do. That should be 1/2. This should be 2. Now, the limit is c goes to 0 from the right side of this function. I mean, this function that we have here, this antiderivative function, is actually continuous at c equals 0, or at least continuous from the right anyway. And so this limit as x approaches 0 from the right is just c equals 0 here. So this should still say 1/2 down here. Let's see, 0 to the 1/2. But of course 0 to the 1/2 is just 0. And so we get we get actually now let me get this right here. Come on. This is not 1/2 here. Okay, let's get this right here. So let's do the power rule again. Add 1 to the power becomes 1/2. We need to multiply by the reciprocal of 1/2, which is 2. So all these where I had a fraction out front, that should just be 2. You guys probably already caught that, didn't you? Okay. 2. And what does that turn out to be in the end? Oh, turns out to be 4. There we go. So that limit turns out to be just 4. And if you look, that's kind of what we kind of saw numerically. And when you start out here, we were at 2 here, and then we were at 2 point something here, and we were at 3 point something, 3 point low something, 3.8 something here. As we got further and further in, it seems reasonable that that limit might be might be 4. And in fact, that's exactly what it is. Now, I want you to think about the geometry of what's happening here. This is going to blow your mind here because this is interesting. This is a finite area. It takes exactly 4 square tiles, 4 1-by-1 tiles to tile this area. It's a finite area. You don't have to go out, let's say if the unit was 1 foot, go out to the hardware store, buy you 4 1-by-1 tiles. You got enough tile to tile it. But there are not enough baseboards in the world to ever go around this region. Because look, you just got a little small region there, you got a finite across here. But both this vertical side and this top are of infinite length. So here we have a region with an infinite perimeter and a finite area. Only need 4 tiles, but not enough baseboards in the whole world to ever go around that thing. It was that infinite perimeter and with enclosing a finite area. Rather bizarre thing happens. And things like that happen all the time. Yeah, let me put the right numbers in here. Okay, very remarkable result. There's a picture of it again there. Okay, let's look at another example. So let's say we got a function, another type of function here. This one, what if we have infinities for our limits here? One of the limits. Well, if a function is continuous on an interval from a to infinity, then the natural thing to do would be to take the improper integral, okay, from a to infinity and say, well, do it from a to c. That's a closed interval from a to c, where c is any number bigger than a. And then that integral is defined, and then take the limit as c goes to infinity. And of course, if you go on, if it's an integral from negative infinity, then you'd have to take this limit as c goes to negative infinity of c to b of f of x dx, where c is anything that's less than b. So it's sort of the same thing. It's just a right. If it's a lower limit, you're going to be taking a left limit. And this time, instead of approaching a constant from the left, we're approaching all the way, letting it go down forever, negative infinity, forever to the left. And of course, this one up here, when it's the upper limit that it's not continuous at, if it's infinity or some constant, we're taking a limit from the left, in this case approaching infinity, which is always a left-handed limit. Okay, and so that's the basic idea. I think maybe let's look at another example here in just a second.